Welcome to lecture 11. I'm Graham Hutton from the University of Nottingham, and I'm very pleased that Erik has invited me to give this guest lecture in his series on programming in Haskell. What you've seen so far in the series is the basics of functional programming in Haskell illustrated using lots of small examples. What I'd like to do today is try and tie some of these ideas together with a larger example of functional programming in Haskell. And the example that we're going to look at is something called the countdown problem. So let's start with the question, what actually is this countdown problem that we're going to talk about? Well, Countdown itself is a popular quiz program which has been running on British television since 1982. In fact, it was the first program to be broadcast on Channel 4 in the UK, and it's been running, I think, every week since 1982. So it's a very long-running program. It's based upon an original French version, which I'm not even going to try and pronounce, but it means basically here the letters and the numbers. And from our point of view, the interesting aspect of the Countdown show is that it includes a numbers game that we're going to refer to as the countdown problem. And what I'm going to show you in this lecture is how to write an efficient program to solve the numbers game from Countdown. So let's introduce the problem by means of an example. So the problem is you're given 6 numbers to start with. So suppose we're given the numbers 1, 3, 7, 10, 25 and 50. And you can use the 4 standard arithmetic operators, so you have addition, subtraction, multiplication and division. And the name of the game is that you've got to try and use the numbers which you're given and the 4 standard arithmetic operators to build a simple arithmetic expression whose value is a given target. So in this case, the game is to build an arithmetic expression whose target is 765. So that's the name of the game. You're given some numbers, the 4 standard arithmetic operators, and you've got to build an expression that has a particular target value. Of course, there are some rules associated with the game as well, so I'll talk you quickly through the rules of the game. The first one is that all the numbers which you're given, and crucially, all the intermediate results that you may construct in your expression must be positive natural numbers. And what I mean by positive natural numbers is simply positive whole numbers, 1, 2, 3, etc. So in particular, you're not allowed at any stage of the game to use negative numbers, 0, or proper fractions. So we can illustrate this using the board. So for example, if at some stage in the game you do 2 minus 1, that's okay because the result is a positive natural number. What would not be okay is if you did 1 minus 2 because the result is minus 1. So that would move out with the kind of domain of the game. You must always remain within the space of numbers 1, 2, 3, etc. Another example would be if you do 4 divided by 2. That would be okay because the result is 2, which is a positive natural number. But for example, if you did 3 divided by 2, that would not be okay because the result is a proper fraction. So again, no negative numbers, you're not allowed to use 0, and you're not allowed to use proper fractions. The second rule in the game is that each of the source numbers that you are given can be used at most once when you're constructing an expression. So if we go back to our example here, you're given 6 numbers, you don't need to use all of them, but once you've used any of them, you can't use it again. So in particular, for example, if you've used the number 1, you can't use it again unless you're actually given 2 copies or 3 copies of 1 in your given numbers at the start. And the last part is that we're going to make some simplification here on the TV show to make the problem interesting and tractable for human players. They make some basic assumptions. So in particular, they only give people 30 seconds to solve the problem, and they impose some constraints on how large the numbers that you're given and the target can be to actually make it tractable. Because we're going to write a computer program to solve the problem, we don't need to worry about such practicalities, so we'll just adopt the 2 basic rules here. So what you might like to do at this point in the video is pause it and see if you can solve the problem for yourself. See if, given these 6 numbers and these operators, and given the rules which I've just talked you through, can you construct the target number 765? So if you think about this for a moment, here's one possible solution. If you take the 25 and the 10 that you're given, subtract them to give 15, and then take the 50 and the 1 that you're given and multiply those to give 51, and then if you can remember your 15 times table from school, which I'm sure you all can, the result is 765, which is exactly the target that we're looking for. You can ask yourself, well, how hard a problem is this? How big is the problem space typically? Well, if you calculate all possible solutions for this example, you'll find that there are 780 different solutions. But of course, many of these will actually be quite similar. And this is an important point that we'll come back to later on towards the end of the lecture. You can also ask yourself, do all such problems have a solution? And the answer is no. For example, if you keep the 6 given numbers the same as the example we've just been thinking about, but you change the target to 831, then you end up with a problem which has no solution. Okay, so this is the name of the game. We want to try and write an efficient program that solves the countdown problem. So let's start doing some Haskell now, and the first thing that we're going to do is think about how to represent and evaluate arithmetic expressions. So we'll start off with a simple data type definition, which we've covered in lecture 10. So here we're defining a data type to represent the 4 different operators. And this data type declaration defines 5 things. It defines a new data type called op, which stands for operator, and then it defines 4 new values, or 4 new constructors of this data type, which represent the 4 different arithmetic operations: addition, subtraction, multiplication, and division. So it's a nice, simple, non-recursive data type declaration, which is just kind of enumerating the 4 possibilities that we can have for an operator. Next, we'll define a little function, which is going to give the meaning to the values of this data type. It's going to tell us how to interpret an operator applied to 2 positive natural numbers. So here we're defining a little function called apply, and it takes an operator and then 2 numbers, and then we'll just do the appropriate thing. And of course, this is just a simple little pattern matching definition. We just have 4 equations, 1 for each of the different possibilities of an operator which we can have, and we just do the appropriate thing. So for example, in the case of add, if we apply the add operator to a number x and y, we just return x plus y. And note that here in the division case, we're using integer division to ensure that we actually get an integer as the output. Okay, so simple data type declaration, simple function which explains how to actually perform one of these operations on 2 numbers. The next thing we're going to do is define a little validity checker. A few minutes ago, I mentioned that one of the fundamental rules of the game is that any intermediate results that you calculate while you're solving the problem must remain as positive natural numbers, 1, 2, 3, etc. No negative numbers, no 0, no proper fractions. So it's quite natural that we're going to have to check for validity when we're building up expressions. So let's define a little function that will do that for us. What valid will do is it will take one of our 4 operators, it will take 2 positive natural numbers, and it will return true or false to say whether when we apply that operator we will get a result which is once again a positive natural number. So again, we have 4 ways of forming an operator, so we're going to have 4 equations in our definition for the function. So let's treat each of these one after the other. So in the case of addition, there's not really anything to check, because if I give you 2 positive natural numbers, like 3 and 5, you add them together, you're always guaranteed to get another such. So we don't really need to even match here. We use the wildcard pattern. Whatever numbers you're given here, if you add them together, you will get another positive natural number. So we just simply give back true in this case. We need to be a little bit more careful in the case of subtraction. If I do 3 minus 2, that's okay. But if I do 2 minus 3, I'm going to get a negative result. So that's not okay. So we need a little test here. Subtraction of x minus y is only valid if x is strictly greater than y. So 3 minus 2 is okay, 2 minus 3 is not okay. Multiplication is the same as addition. If you multiply any two positive natural numbers, you get another one. 2 times 3 is 6, so that's okay. In the case of division, what we need to check is that the remainder, when we divide one by the other, is 0, to check that we actually have, we don't have, sorry, a proper fraction. So 4 divided by 2 is okay, because the remainder is 0. 4 divided by 3 is not okay, because the remainder is 1. So here we're using the Haskell mod function, which performs a division, gives you back the remainder, and we test to see if it's 0. Now we can define a little recursive data type to represent arithmetic expressions. And again, recursive data types is something that you've learned about already in lecture 10 or chapter 10. So we're defining a type to represent arithmetic expressions, and there are two forms of expressions. Either we have an integer value, so we have the val tag for that purpose, or we have the application of an operator to two sub-expressions. So we have an application tag, an operator, and then two sub-expressions. So if you think about what's being defined here, again, it's a data type. Think about what kind of things are being defined. Here we have three things being defined. We're defining a new data type called expr, and two new constructors for the data type. One called val, which takes an integer and builds you an expression, and one called app, standing for application, which takes an operator, an expression, and then another expression, and then builds you a new expression. Okay, so I'll give you a little example of this to explain how this recursive data type is working. So if I wanted to represent, for example, 1 plus 2 as a value of this data type, what I would do is, it's going to be an application, because that's the thing at the top here. So we'd write app. Then the operator is addition. And then we have two sub-expressions. We have val1 and val2. And these two expressions represent the two numbers here. An important point, and where people sometimes go wrong with things like this, is if you simply write apply add to 1, 2, this won't be correct because it's got a type error. These two things here are integers, but if you look at the type of the app operator, it requires an operator, which add is, and then it requires two sub-expressions. But these are integers, these are not expressions. So that's the reason why we have the val constructor, which is really, if you like, converting an integer into a piece of data as an expression. Okay, so this is the way that we are representing arithmetic expressions. Okay, so the next step is we're going to think about evaluating an arithmetic expression in our data type to give a number. So we'd like to write an evaluation function, and it's going to take an expression as input, as we would expect, but it's got a bit of a strange output type. We might expect it to just return a single integer, but here it's actually returning a list of integers. So why is this the case? Well, if you read the box at the bottom, this function is either going to succeed and return a list with one number in it, which is our result, or it's going to fail and return the empty list. And it may fail because of this constraint that we're not allowed to use 0, we're not allowed to use negative numbers, and we're not allowed to use proper fractions. So when we're evaluating an expression, if we go outside the realms of positive natural numbers, then we're going to need to fail. And the way we're representing failure here is the same way that it was done in the lecture on parsing. You can remember back to the parsing lecture, parsers can fail. If they fail, we return an empty list of results. If they succeed, we return a list of results with one thing in the list. And we're doing exactly the same thing here. So how does our function work? Well, here we're making very good use of the list comprehension notation. So let's see how it works. So an expression has two possible kinds. We have a value or an application, so we have two equations to deal with this. So in the value case, what we might have expected to write is something like, if you evaluate a value, then you do a test. If the value is greater than 0, then we'll just package it up. Otherwise, we will fail. Okay, this is a perfectly valid definition, but we can write it in a more compact way by using the list comprehension syntax. So over here we're forming a list of the value n such that, or provided that in this case, n is greater than 0. So here we have a list comprehension which just simply returns the value n provided that n is greater than 0. And this has the same effect as this code here. So here we're leveraging the power of list comprehensions to make our program a little bit more compact. We really see the payoff of using list comprehensions when we look at the application case. So in this case, what we're going to do is, if you have an application of an operator O to a sub-expression L and a sub-expression R, what you want to do is evaluate the left sub-expression, and if that succeeds, call its result x. Evaluate the right sub-expression, and if that succeeds, call its result y. And then what you want to do is check, is the application of the operator O to the sub-expressions x and y, or sorry, the integers x and y, is that valid? Because that may fail, maybe negative or 0 for example. And if all of these things succeed, what you want to do is actually perform the application of the operator to the two numbers. So what we're seeing here is that list comprehension is really hiding all of the failure propagation from us, because this could fail, or this could fail. Any of these three things here could fail, and the list comprehension machinery is taking account of failure and propagating it for us automatically. So if any one of these things fails, this will return the empty list. Otherwise it will return a list with one thing. Some of you who have maybe thought a bit more about Haskell or got a bit more experience with Haskell might be thinking, why didn't I do this with the maybe type? Well, I could do that, and then I would have to use the monad syntax, the do syntax, but I wanted to keep it a little bit simpler here, so I've used the special case of the list comprehension syntax. So here we have then a little evaluation function. So what we want to do now is, before trying to solve the problem, let's think about what it actually means to solve the problem. Let's think about formalizing the problem. And in order to do this, we're going to define a couple of helper functions first of all. And the first one is a function that I'm going to call choices. And what choices does is you give it a list of things, and it returns a list of all possible ways of choosing 0 or more elements from that list. And you can see what it's doing from its type, or its type tells you something about what it's doing. Choices takes a list of things and gives you back a list of lists of things. So for example, suppose we were given two numbers, just 1 and 2. If we apply the choices function to this, the output we expect in some order, I'm not really bothered about the order here, is you could choose no elements, so just get the empty list, or you could choose the 1 or the 2, so get 2 singleton lists, or you could choose 1, 2, or you could choose 2, 1. Okay, and the reason we're going to need this function is because, if you remember the rules of the game, we can use any of the 6 given numbers in any order, but we can only use each one at most once. So the choices function is really taking account of the fact that if I give you, for example, 2 numbers and say, how can you choose numbers from those, then the choices function gives you the right result. I'm not going to show you how to implement this. I'll leave that as an exercise for you. But you can also look on the code for this, which is available online, and see how the choices function is defined. I think it's defined using a list comprehension, but there's many different ways that you could define this function. The other helper function, which I'm going to use, is simply going to extract all the values from an expression. So I'm going to define a function called values, and it takes an arithmetic expression as its input and gives you back all the numbers which occur in that expression. And this is just a simple application of recursion. We have 2 equations which follow the structure that an expression can have. So an expression can either be a value n, in which case we just turn that into a singleton list with n itself sitting in the list, or it can be the application of an operator. And we don't care what the operator is, because we're only interested in collecting all the values or numbers in the expression. So let's not match on that. Let's not give it a name. Here we have a left sub-expression and a right sub-expression. All we're going to do is recursively calculate all the values in the left sub-expression. That will give me a list of numbers. Recursively calculate all the values in the right sub-expression. That will give me a list of numbers, and then I just concatenate or append the two lists together using the append operator in Haskell. So it's a nice kind of simple example of recursive definition over expressions, which follows the precise structure of expressions in a natural manner. So putting all this together now we can define a little function which specifies what it means to solve an instance of the countdown problem. So we're going to define a function called solution, and it takes three inputs. It takes an expression which you think solves the problem. It takes the 6 given numbers packaged up as a list. It takes the target number, and it returns true or false depending on whether that given expression actually solves that particular problem or not. So how do we do this? Well, suppose we call our expression E, we call our source numbers n's, and we call our target number n. All we're going to do is check that the values in the expression are selected from all the possible choices that we could make. So choices here takes the 6 numbers, returns all possible ways of choosing 6 numbers. Now what we're going to do is take all the values out of the expression and check if this list is an element of all the lists produced by this choices function here. So this is potentially very inefficient, but we're not caring about this. This is not a function we really intend to run. This is a specification which we're using to understand the problem a little bit better. Okay, so this is just saying we've used the numbers in the correct way. We haven't used any number more than once in particular. The second part says that the expression actually solves the problem. So here it's just logical and in Haskell, and this is saying if we evaluate an expression, we will get a successful result, which is precisely the number that we were given. Okay, so this is taking account of kind of one of the rules of the game, which says you can use any of the numbers at most once in any order, and this is saying when you evaluate, you must get exactly the target that you're looking for, and you mustn't go -0 or a proper fraction at any point. So now we have a nice kind of essentially one-line description. Doesn't quite fit on the slide, but it's a one-line program that specifies what it means to solve an instance of the countdown problem. So what we're going to do now is start to think about how to solve the problem. And we're going to come at this in a series of steps. We're going to start off with a simple but inefficient solution, and then improve it in a series of steps and end up with a highly efficient solution at the end. And the first way we're going to solve the problem is just by brute force. We're just going to enumerate all possible expressions that we could generate using the given numbers, and then mechanically test each of these one by one to see if it actually solves the problem. So again, we're going to use some helper functions before we actually write the program that we're interested in. And the first helper function we're going to use is a function called split. And I think it's easier if we start off down here by the example, with the example. So what split does is you give it a list of things, and it returns all possible ways of splitting that list into 2 parts which are non-empty. So in this case we're given 4 numbers, so we could split off one number. We could split off the 1 and then have 2, 3, 4 left. Or we could split off 2 numbers, we could have 1 and 2, and then the 3 and the 4 left. Or we could split off the first 3 and then have 1 number left at the end. Okay, so we can now understand the type of split is it takes a list of things, doesn't care that it's numbers, and it returns a list of pairs of lists. Okay, and again, I'm not going to show you how to define this one. There's various different ways to define this. You can find it in the code, which is available online. But you can also try and define this yourself as an exercise. Maybe start by defining it using take and drop. This is probably the key function in the lecture. This is really the key thing which is going to make everything work fundamentally. And what this function does is you give it a list of numbers, say the 6 numbers which are given to try and solve the countdown problem, and what it will do is build you a list of all possible expressions whose values are precisely that list of numbers. So if you give it the 6 numbers that we're starting with, it will give you all possible expressions whose values are precisely those 6 numbers in that order. So there's 3 cases here. The first one says if you give me no numbers, then I can't build you any expressions, so I will work like this. Actually, I think I'll just close the blinds here because it's getting a bit sunny. And that should be better. So the first case, if you give me no numbers, I will give you no expressions back. The second case is if you give me a single number, what expression can I build over that? Well, there's only one expression that I can build, it's the number itself. The interesting case is when we have two or more numbers and we want to build all possible expressions whose values are precisely those list of numbers. And the way we do that is again by leveraging the power of list comprehensions. What we're going to do is take our list of numbers, maybe 6 numbers, split it up into non-empty parts in all possible ways. That's what the split function does. Then we're going to recursively calculate all the expressions over the left list, all the expressions over the right list, and then combine all those possible expressions in all possible ways to give expressions which we'll then package up at the end. So there's quite a lot of things going on here. You may need to kind of pause for a moment and think about what's actually going on, but essentially we're taking 6 numbers, say, splitting them up into non-empty parts in all possible ways, sending the first part down the left side, the right part down the right side, considering all expressions that we can build for these, and then combining these expressions in all possible ways. So again, we're leveraging the power of list comprehensions to do a quite sophisticated computation, but in a simple way. So we need another little helper function here called combine, which is used at the end to combine solutions. And all combine does is you give it 2 expressions and it builds the 4 possible arithmetic expressions that you can get by sticking the 4 possible arithmetic operators at the root of an expression tree. So again, we can just use list comprehensions to do this. If I give you an expression called L, an expression called R, I set up a little loop. I'm going to range O for an operator over the 4 operators here, add, subtract, multiply and divide, and we just package up an application of the appropriate operator to L and R. So this is just taking 2 expressions and forming the 4 possible expressions using the 4 possible arithmetic operations. So now we can define our first solution checker, just using these simple functions which we've been writing. So our solution finder is going to take 2 inputs. You give it the 6 numbers that you're given at the start of the problem. You give it the single target number which you want to reach, and it will give you back all possible expressions which solve that particular problem. So in the case of our example problem at the start, it will give you all 780 different expressions which solve that example problem. So how does it actually work? Well, suppose we're given a list of numbers n's and a target number n. What we'll first of all do is use our choices function to select all possible ways of selecting 0 or more numbers from the 6 numbers that we're given. So all possible permutations of selecting any number of numbers that we like. Then we'll use our expressions function to take each choice list and generate all possible expressions whose values are exactly that list in the precise order in which it's given. Okay? And then we'll do a test at the end. We'll check if evaluating the expression gives exactly the target number that we're looking for. So again, we're using the power of list comprehensions here. We have 2 generators at the start. We generate all possible choices from the list of 6 numbers, which will be a large list. Then we generate all possible expressions over each of those choice lists, which will be a large list again. And then for each of those expressions which we get, we're going to test, does evaluating that expression give success with exactly the target number that we're looking for. And only in that case do we return that particular expression E. So again, this is essentially a 1-line program which will solve the countdown problem. So, key question now is, how fast is this? Is this fast enough to actually be tractable and usable in practice? So let's look at some performance figures. So at the point when I wrote the book, this was a reasonable specification laptop. It was a 1.2 GHz Pentium M laptop, and I was running GHC version 6.4.1, so I used a compiled version of Haskell to get the maximum performance possible. The Hug system isn't really fast enough to be doing this kind of thing, so I used the Glasgow Haskell compiler. If you just look at the example we had at the start of the lecture, call our solutions function. You give it these 6 numbers as your source numbers. You give it this target number as your target, and it will find all possible solutions for you. So how fast does it work? Well, it finds one solution in about a third of a second, which is great. That's just basically as soon as you press the return key, it will find one. And it finds all 780 solutions in about 45 seconds. So on the face of it, this looks great because if you remember on the TV show, you've got 30 seconds to try and solve the problem. So here, we're finding one solution, which is all we really want really, in a third of a second. But this is not satisfactory because of this result here. Potentially, for some problems, there may only be a small number of solutions and they may be towards the end of the solution space rather than near the beginning of the solution space. And what this result down here is telling us is that potentially we may need to take up to around a minute to find even one solution if that one solution happened to live right near the end of the solution space. So for this particular problem, this brute force search approach works fine because we get one solution in a third of a second, but potentially this program may take a minute, or in some cases I think actually even a couple of minutes, to find even one solution. So this program isn't good enough. So how can we do better? So we do better by thinking about the problem domain. So an observation at this point is that many of the expressions which we're generating using our brute force generate and test approach will be invalid. And what I mean by invalid is that they will fail to evaluate. So again, remember, if we construct an expression which involves negative numbers or zero or proper fractions, that will fail to evaluate. And if you do some simple statistics, for the example which we had at the start, we've just seen how to solve, there's 33 million expressions which you can generate over those 6 given numbers, but only 5 million of those expressions are actually valid. So about 1/6 of the expressions that we're generating actually have any chance of being a solution in the sense that they satisfy the constraints of the game about not being negative, zero, or a proper fraction. And the idea here now is a classic example of program fusion, where you want to kind of take two things which are done separately and fuse them together to do them in a more efficient way. So what we'd like to do in this case is we'd like to combine the generation of expressions together with their evaluation in the hope that we can avoid generating quite so many invalid expressions. And in particular, what we want to avoid is generating invalid expressions which are then used to generate more invalid expressions because we have a recursive algorithm. So it's an example of fusion. So we can draw a little picture at this point to illustrate what we're trying to do. Essentially we have a generate and test approach at the moment. We have an expressions function which is generating expressions, and those are being fed into an evaluation function which is evaluating them. And the problem is that many of the expressions that this thing generates will be invalid, and then this thing will reject them. So what we'd like to do is program fusion. We'd like to combine these two into one function, which I'm going to call results, which does both things at the same time. Okay, this is a classic example of program fusion, doing two things separately, try and combine them to achieve the same result, but in a more efficient manner. So I want to be clear about what we're trying to do here. So here's a little specification for what we'd like to do. So first of all, we're going to define a little result type, and result is going to be a pair of a valid expression, so one which evaluates without any problems, doesn't go zero, for example, and its resulting value. Okay, so a result is just simply packaging up an expression which is okay, doesn't fail, and having its value there alongside it as well. Then what we'd like to do is we'd like to define a function called results, which takes a list of numbers in and builds us all possible results over that number. And you can see that we want it to be able to do some kind of fusion in the sense that it should satisfy this specification here. If you give it 6 numbers, what it's going to essentially do is have the same behavior as calling the experts function to generate expressions, and then it's going to call eval to evaluate them, and then if that's successful, it will package up the two things. This will be a valid expression and its resulting number. Okay, but if we simply implemented results like this, we wouldn't get anywhere because we haven't done any fusion yet. This is the expressions function and this is the eval function that we started with. What we want to do is fuse them together to get a new function called results, which has this behavior but is defined independently of the original expers function and the original evaluation function. So it turns out to be quite simple to do this. Here's the way results is defined. It's defined using exactly the same pattern of recursion as the expers function, but it does a little bit more. So let's talk through each of the cases. So the base case is the same. If I give you no numbers, there's no results. You can't build any expressions which successfully evaluate. So there's nothing to do there. If I give you one number, then I need to check, is the number that you give me okay? So is it a positive natural number? If it is, I package up the expression and I package up the result of evaluating that. So that's a nice easy base case. The recursive case has exactly the same pattern of recursion as the expers function earlier in the lecture. The only point of difference is that now we need to combine results rather than combining expressions. So the definition here is exactly the same, except we make recursive calls to results, and we need a new combine function which takes two results and gives you all possible expressions that you can form by combining those results using the four different arithmetic operators. So this is the point really where things are a little bit different. So what the combine prime function does is it takes an expression L, which is valid, and its value x, which is a number, an expression r, which is valid, and its value y, which is a number, and then it's going to do a bunch of things. First of all, it's going to select each operator from the list of all four possible operators, add, subtract, multiply, and divide. It's then going to crucially check, is it valid to apply that operator to the number x and the number y. And remember, x is the result of evaluating the first expression, y is the result of evaluating the second expression. So in order to put these together using a particular operator, we need to check, is that a valid thing to do? So we have a little validity check here. If this returns true, we will package up the two expressions with the operator, and we will apply our application function to calculate the resulting integer. Okay, so this is kind of doing a couple of things at the same time. So putting all this together now, we have a new countdown problem solver which works by not generating all possible expressions and then testing them. It's kind of fused together the process of generating and testing into this new function called results. So how do we package this up together? Well, we define a new function called solutions prime. Has the same type as before. It takes a list of numbers, which we're given, 6 numbers. It takes a single target number, which we're trying to reach, and it will give us back all possible expressions which solves this particular instance of the countdown problem. So how does it work? Well, given 6 numbers n's, given a single target n, we start off with the same as before. We consider all possible choices from these 6 numbers, so this will construct a large list of all possible choices. But now we simply call results. We call results with each of these choice lists, and we will get a valid expression e and a resulting number m. And all we need to do then is check, is the number m here equal to what we want? If it is, we keep the expression. So again, it's a nice one-line program which is solving the countdown problem. Spread it out over 3 lines for kind of readability here, but essentially, again, it's a one-line program. So we can ask ourselves, how much difference does this make to the running time of the program? And as we'll see, it makes quite a significant difference. So let's try the same example, but call our new solution finder, which fuse together the generation of expressions with their evaluation. What we find now is that we get basically a 10 times speed up. So previously we found one solution in about 1/3 of a second, or the first solution in 1/3 of a second. Now it's 4/100ths of a second, and previously we were finding all solutions in about 45 seconds. Now that's gone down to less than 3 seconds. So essentially we've got a 10-fold speed up in both of these cases here, which is really quite a significant speed up. My research work is to do with program fusion, and for me this is one of the most compelling examples which I have seen about program fusion. It's the idea of putting programs together, trying to fuse their behaviours together to get an increase in efficiency. And here we see a very compelling example of this. We took a program which didn't satisfy our time demands. It took more than 30 seconds. We do a simple fusion and we get a factor of 10 improvement, which is really quite significant. So at this point, this is now sufficient to solve any instance of the countdown program from the TV show, but let's think a bit further. Can we make this even faster? It's still a bit disappointing that a kind of reasonable specification laptop is still taking almost 4 seconds to find all 780 instances of a solution to this problem. So can we do better? So a key observation here, and this is a point which I was alluding to at the start of the lecture, is if you think about the problem we've been looking at, which had 780 solutions, of course many of those solutions will be essentially the same. They'll just be simple arithmetic rearrangings of other solutions. So let's try and exploit these arithmetic properties to make our solution finder even faster. So the observation here is that many of the solutions will be essentially the same just by applying properties like x times y is y times x. So if you have 2 times 3, that gives the same result as 3 times 2. So multiplication is commutative. And for example, x times 1 is the same as x. So 1 is the identity for multiplication. If you have 3 times 1, that's going to just give the same result as 3. So there's really no point in considering all possible kind of combinations of ways of rearranging expressions using these simple arithmetic properties. So the last improvement we're going to make to this program is that we'd like to exploit arithmetic properties like this to reduce the search space and thereby also reduce the solution space and hopefully make our countdown solver run even faster than previously. So it turns out there's a really simple trick to making this the case, to exploit these kind of arithmetic properties. And it's basically to modify the definition of our validity checker. So remember what the validity checker did is it took one of the 4 arithmetic operators, it took 2 positive natural numbers, and it returned true or false to say whether the result would be a positive natural number as well. Here's the definition which we started with. Let's modify it now to take account of these simple commutativity properties to say that addition and multiplication are commutative. It doesn't matter in which order you do them, and simple identity properties as well. So here's the first modification. Rather than saying that addition is always valid, what I'm going to say is addition is only valid if the first thing is less than or equal to the second thing. And the reason for this is I want to accept expressions like add 1, 2, that's going to be okay, but I want to reject this one, because if I generate add 1, 2, I know I'm also going to generate add 2, 1 because I'm considering all possible rearrangings of the numbers which I'm given. So I don't really need to consider this one, where the first one is bigger than the second one, because I know I'm also going to consider this one. So the way I'll take account of commutativity is I'll say you're only allowed to add 2 numbers if the first one is less than or equal to the second one. Okay, so that's a little trick to account for commutativity of addition. We can do the same with multiplication. So we're only going to allow multiplication to take place if the first number is less than or equal to the second one. So 2 times 3 will be okay, that will give 6. We'll say 3 times 2 is not okay, that will also give 6, but we'll already have seen the 2 times 3, so let's throw away the 3 times 2 to take account of commutativity of multiplication. We can also do something else with multiplication. We could put on 2 further side conditions that say that multiplication is only valid if both of the arguments are not 1. Because if you try and do 3 times 1, there's no point in doing that because you'll just get the same result as 3. Similarly, if you do 1 times 3, you just get 3. So we'll put 2 extra conditions on here to say that the first argument had better not be 1 and the second argument had better not be 1 as well. So this is taking account of, in a really simple way, the fact that 1 is the unit for multiplication. Similarly, we can take account of the fact that there's no point in dividing by 1, because any number divided by 1 is itself, by putting on an extra little condition down here, which says that the second argument to division had better not be 1. Okay, so it's a nice little change we've made here. We've taken account of some simple commutativity and identity properties of some of the operators just by making some very small changes to our validity checker. So the question now is, how much of a change does this make to our actual countdown solver? So if we implement a new countdown solver based upon this new validity checker, let's call it solutions double prime. Let's apply it to our same example, and first of all ask ourselves, how does this reduce the search space and the solution space? Well, it reduces the search space considerably because the number of valid expressions now reduces from previously being about 5 million down to 250,000. So we've divided our potential solution space, search space, sorry, by about 20. And it reduces the number of solutions dramatically as well. Previously we had 780 solutions to this problem. Now we have 49 solutions, which is about 16 times less. Okay, so the space of expressions of the search space and the solution space is getting dramatically smaller, about 20 times less in each of the cases here. So crucial figure is how much faster does this actually run? Well, in terms of finding one solution, it runs about twice as fast. It was 0.04 of a second before, it's now 0.02 of a second. The real gain is when we consider generating all solutions. So previously, I think it was about 3.5 seconds to find all the solutions using our second countdown solver. Using our final one, we can find all possible solutions in less than half a second, which is really excellent now, and about 7 times faster than what we had before. So I've only shown you one example here. You can ask yourself, how does it perform in practice? Well, in practice, if you give this countdown solver any problem which can possibly arise on the TV show, using the constraints which they have about the numbers not being too big, etc., then it will find one solution as soon as you hit the return key, if you use the Glasgow Haskell compiler, and it will find all solutions in less than a second. So this is a very nice program now that solves the countdown problem. So that's it for the lecture. Just to kind of summarize what we've done, we've considered a simple but interesting numbers game and tried to write an efficient Haskell program to solve it. And the strategy that we had is something which occurs all the time in functional programming. You start off by trying to understand the problem, so I wrote a little specification for what it means to solve the problem, and then I wrote the simplest possible solution finder which I could think of. It was a kind of brute force generate and test method, just generated all possible expressions and then evaluated each of them and tested if it's a solution. That wasn't fast enough in practice, so then I refined it in a couple of steps by thinking more carefully about the problem domain. So we did two things. We fused generation and testing together and got a 10 times efficiency gain. And in the second step, we took account of some simple arithmetic properties about the problem domain, the fact that we have some simple commutativity and identity properties, and again we get more or less a factor of 10 improvement in speed of our program. So it's really quite a dramatic improvement we've got here. We took a simple but inefficient program, improved it in 2 steps, and ended up with really a highly efficient program to solve the countdown problem, which is about 100 times more efficient than what we started with. Okay, so I hope you've enjoyed the lecture. If you'd like to find out some more information about this, I didn't show you all the code here. There was a few helper functions which I didn't show you, and there's some I/O wrapped around this to actually make it usable in practice. If you'd like to get the code, if you just do a search for programming in Haskell, you'll find the books webpage. You can download the code for this example there. If you'd like to know even more about this, and in particular if you'd like to see a proof of correctness of each of these 2 transformations, if you do a Google search for the countdown problem, you'll find a research article which I wrote about this, which goes into all the gory details about how one might actually prove that the final program we've got actually works correctly. So that's the end of the lecture. I hope you've enjoyed this. This is my favourite chapter of the book, and hope to see you again sometime soon.